Okay, can you hear me now?
Yes, I can. Thank you.
Okay, sorry about that. I wanted to welcome the participants along with Courtney to the webinar, and thank you for your interest in the Higher Capacity Manual. I believe I speak for many in saying that we're pleased with the 6th edition of the Higher Capacity Manual. And as Courtney mentioned, I am the past subcommittee chair for the Urban Streets chapters, and I'm particularly proud and pleased with the additions and changes that we've made to the Urban Streets methodology. The updates provide us with methodologies that are capable of handling increasing complexities in our transportation network. The Higher Capacity and Quality of Service Committee, as well as the Urban Streets Subcommittee, have worked closely with the NCHRP 3-115 team to ensure that the material that were provided in the Higher Capacity Manual, including the Urban Streets chapters, they're not only science and empirically based, but as one of our subcommittee members often stated, that the methodologies and their results needed to pass the sniff test. The methodologies had to produce results that were observable in the field. The Urban Streets Subcommittee worked with the 3-115 team to identify and prioritize the updates that were needed for the chapters. And where research had been performed to address areas of needs within the chapter, this research was reviewed, it was discussed, had lots of discussion, and then a determination made on whether or not it should be incorporated into the 6th edition. And in some cases of high priority needs within the chapter, new research was performed and the results were vetted by the Urban Streets Subcommittee as well as the Higher Capacity and Quality of Service Committee. Urban Streets as a facility has a high priority within the Higher Capacity Manual. We've got several chapters that are devoted to this topic. There's the Urban Streets Facilities chapter that describes concepts and methodologies for evaluating an urban street facility, as well as another chapter that looks at segments. We've got a chapter on urban street reliability and ATDM. There are supplemental chapters for both urban street facilities and urban street segments, which give information about the use of alternative evaluation tools. It gives details on the methodologies and provides planning level analysis methods, as well as chapters on unsignalized, signalized intersections, and well as roundabouts. We've heard of some of the outside tools outside of the HCM that can also be used, including the HCM Applications Guide in Volume 4, the Planning and Preliminary Engineering Applications Guide. It's another resource that's available that shows users how to incorporate the chapter's methods and performance measures into a planning effort. We believe the HCM plus these resources provide you, the traffic engineer, with a good toolbox for evaluating all the aspects of our urban streets. One of the features of the Urban Streets chapters that was introduced in the 2010 HCM and continues in the HCM 6th edition is the provision of a multimodal evaluation. The multimodal evaluation allows for not just evaluating the operation of cars on the roadway, but also provides an approach to determine the operation of bicycles, pedestrians, and transit within the right-of-way. And part of our discussion will be looking at that today. Today's presentation will provide a discussion on HCM multimodal performance measures as applied to a complete streets analyses. I really hope that you will not only gain an understanding of the methodologies, but you will continue to then apply the methodologies to an even wider array of urban street conditions. We do welcome your feedback and hope that you will help us to continue to make the HCM a valuable resource for transportation professionals. We also encourage you to participate in the Higher Capacity and Quality of Service Committee and within the subcommittees. We thank you again for your interest in the Higher Capacity Manual, and we hope to see you in future meetings and future webinars. Thank you.
Hi and welcome everybody. I'm Paul Reyes and I'm going to be presenting for the first half of this webinar. Today we're going to be talking about 5 main topics. The first is going through and describing the different urban street system elements that are defined in the Highway Capacity Manual. Things like segments, facilities, boundary intersections. What are those things and how are they defined? Next, we'll look at the full range of multimodal performance measures that can be evaluated for an urban street in the Highway Capacity Manual. Then we'll move on to looking at one specific performance measure, or set of performance measures, the modal perception scores that can be evaluated for transit passengers, pedestrians, bicycles, and automobile travelers. And these perception scores are really the heart of the multimodal evaluation process in the Highway Capacity Manual, and what can be used to support a complete streets analysis. Aaron will give some application examples. We have 3 case studies of how these measures have been applied to actual projects. And then we'll provide a summary of the webinar and provide information about future research needs and resources that are available for people who want to know more about this method. So we'll start first by going through the different urban street system elements that are defined in the Highway Capacity Manual. So there are 4 main types of urban street elements. Obviously, one of the things you can find along a street are intersections. They can be signalized intersections, stop-controlled intersections, roundabouts, interchange ramp terminals, and alternative intersections. And these are all covered in chapters 19 through 23 in the Highway Capacity Manual. These are the focus of the next 2 webinars, numbers 6 and 7. So we won't go into great detail about intersections in this webinar other than to describe how they fit into a multimodal analysis of a larger urban street. One step up in the hierarchy of urban street system elements are links, which are the section of street between major intersections. You can also do an analysis of what we call a segment, which is the combination of a link and a boundary intersection at the end of the link. And then finally, you can combine multiple consecutive segments together to evaluate the urban street as a facility. We've already looked at urban street reliability as part of webinar 4, and the final webinar in the series, webinar 8, will look at urban street facilities in more detail. So the main focus of this webinar will be on the links and segments, although we will also cover intersections and facilities to the extent that they are incorporated into a multimodal analysis. So the first system element I want to talk about are boundary intersections. Boundary intersections divide an urban street into segments, and the HCM defines these as any intersection where traffic control can require the street's traffic to stop or yield. And these are typically traffic signals, roundabouts, or always stop controlled intersections. In the case of the urban street in the aerial photo at the bottom of the slide, there are 2 signalized intersections that are the boundary intersections for this segment. And we're going to use this particular section of street quite a bit during this first half of the webinar to demonstrate different aspects of the method and different definitions. Now, this definition of boundary intersection does not include signalized crosswalks, signals at fire station driveways, railroad crossings, drawbridges, or other similar places where you might occasionally find traffic signals. And you might also say, well, what about crosswalks? Those can provide a legal obligation to traffic to stop or yield. And that is actually true, but for the purposes of the HCM definition, crosswalks do not create a break or a boundary intersection. Boundary intersections are just one kind of intersection that you can find along an urban street. And boundary intersections being the major intersections where both the major street traffic and the side street traffic may have to stop. The HCM allows you to analyze the operations of both the major street and the cross street. But there are other intersections along an urban street that aren't boundary intersections. These are, for example, intersections where only the side street is stop controlled. You also have a number of driveways typically along an urban street. And at these locations, the HCM will allow you to the turning movements onto and off of the major street, as well as movements crossing the major street, whether they're automobile or pedestrian movements. The analysis of intersections in general will be the topic of webinars 6 and 7. Continuing on, the next type of system element are links. And these are the portions of a street in between boundary intersections. And as you can see here, we have links in both directions of the street. In this case, north is on the right-hand side of the picture. So we have a northbound link and we have a southbound link. And it looks at the operation of the street in between the two signalized boundary intersections. Links, as we'll see, are particularly used in pedestrian and bicycle analysis, but not really for motorized vehicle or transit analysis. And we can take segments, we can take links and their boundary intersections and combine them into segments. And segments are measured from the stop bar of one intersection or one boundary intersection to the stop bar of the next boundary intersection. So you can see there's a little bit of difference depending on which direction you're looking at. Which boundary intersection are you looking at in terms of evaluating the performance of the segment as a whole? So for the southbound or right to left portion of the street, we're looking at what happens when you are able to enter that first intersection, continue down the street, and then, for example, if you're looking at travel time down the street, how much delay do you experience at that downstream intersection before you can actually enter it? So for an urban street analysis, each street direction is analyzed separately for each mode. Finally, you can combine multiple consecutive segments together to form a facility. And the general guidance that the Highway Capacity Manual provides on starting a new facility is when a change occurs in one of these characteristics, or a significant change occurs. A change in the cross-section, particularly the number of through lanes, a significant change in the traffic volumes, a change in the density of land uses along the urban street, or changes in the posted speed, or vehicle speeds in general. So here we have, for example, 5 segments that form a facility. We break the facility on the right-hand side because you have an adjacent freeway with ramps that change the traffic volumes along the street. You also have a rapid transit station there and some larger retail along the street than you have along the rest of the street. So it would be a good place to break the street and start a new facility. So which system element should you study when you're doing an urban street analysis? And the answer to that question depends on what the study area is for analysis and what the purpose of your analysis is. For example, if you're preparing an access management plan or conducting a multimodal corridor analysis, you would typically look at a facility and all of its sub-elements, the segments and the boundary intersections. If you're doing a traffic impact study, you typically look at the intersections along the street, and depending on the requirements of the jurisdiction where you're performing the traffic impact study, you might also need to look at segments. If you're doing a district or a citywide pedestrian and bicycle plan, you might just look at links if you're interested in evaluating the operation or of the quality of service of the pedestrian and bicycle network on a large scale, where you don't want to put a large amount of effort into any one street section, but want to look at a large area as a whole. You might look at links. If you're doing a more narrowly focused plan, then you might also look at intersections and segments. Now that we've defined the different system elements that make up an urban street, we'll take a look at the full range of multimodal performance measures that the Highway Capacity Manual provides. So you can see on this slide that there are 4 modes that the HCM covers. One is the motorized vehicle mode, which we show with a car here. There's the pedestrian mode, the bicycle mode, and the on-street transit mode. Now for this slide, we're going to look at performance measures for facilities and segments. And some of the common performance measures that the Highway Capacity Manual provides are average travel speed. The Highway Capacity Manual also provides a perception score, and we'll get into detail about what a perception score is a little bit later in the webinar. But for right now, just think of it as the average rating a group of people would give a facility or a segment if you were to ask them to rate that segment's operation on or quality of service on a scale of A to F. The HCM can also provide a level of service letter, and for some of the modes, it can provide some other useful performance measures. So let's start off by looking at the motorized vehicle mode. The Highway Capacity Manual provides travel speed, provides a perception score for automobile travelers. It provides a level of service letter, which is based on travel speed, so that's why it's shown in green, to show that in this case travel speed is what is used to determine level of service for the auto mode. It also provides a couple of other performance measures. One is the stop rate. How often does a car have to stop on average while moving down a segment or a facility? And that's measured in number of stops per mile. And at a facility level, the Highway Capacity Manual will also report the critical facility volume to capacity ratio. That is the highest volume to capacity ratio of any boundary intersection along that facility. And if any of those VC ratios exceed 1, then the level of service for the facility is automatically set to F. That's why that performance measure is shown in green. For the pedestrian mode, the HCM could also predict an average travel speed, considering the delay at the boundary intersections in addition to the time it takes to actually travel the length of a segment or a facility. It can produce a perception score for the pedestrian mode and a level of service letter based on that perception score. For pedestrians, there's also a measure of pedestrian space, how much area is provided on average per pedestrian. Pedestrian space is also a component of the level of service for a facility or segment, but as we'll see a little bit later on, it really only comes into play on really heavily used pedestrian facilities where you have, for example, 1,000 or more pedestrians per hour on that facility. The rest of the time, it's the perception score that drives the level of service for pedestrians. For the bicycle mode, it's similar to the pedestrian mode. You can calculate an average travel speed, and you can generate a perception score and a level of service letter based on that perception score. Finally, for the transit mode, again, you can get an average travel speed, a perception score for transit passengers, and a level of service letter based on that perception score. The HCM also produces a segment weight ride score, which is basically looks at how much additional ridership might you expect on a route compared to a baseline case. So, for example, a weight ride score of 2 would indicate that the route would be expected to generate about twice as much ridership as a route that only ran once an hour and had a perceived speed of 15 miles an hour. Looking at links, there are no measures for either the automobile or motorized vehicle mode or for the transit mode. As I said before, links are really only used in pedestrian and bicycle analysis. In this case, for both modes, the HCM reports a perception score and a level of service letter based on a perception score. And you can also calculate a pedestrian space, area per pedestrian for pedestrians. Moving on now to the intersection measures. Now, when we look at intersections, the transit mode is combined with the rest of the motorized vehicle mode. So basically all the delay, for example, that the bus is experiencing is also experienced by all the passengers on the bus. So there's not a separate distinction made for the transit mode when we get to the intersection level. So for buses and automobiles, the HCM can measure average control delay, and it can generate a level of service letter based on that delay. It can also calculate the volume to capacity ratio for the signalized intersection. Again, if that ratio is greater than 1, then the level of service is automatically F. And the HCM could also generate various queuing measures, like the average queue, the 95th percentile queue, the queue storage ratio, which is the how much of the available queue storage, for example, in a left turn lane is being used. So all those kinds of measures relating to queues can be generated for signalized intersections. For the pedestrian mode, again, you can generate average control delay and a level of service based on that. You can also evaluate the amount of pedestrian space provided on street corners as pedestrians wait to cross the street, as well as within crosswalks. And there's a separate pedestrian perception score for signalized intersections. That gets combined with the pedestrian perception score for links to generate the overall pedestrian score for segments. For bicycles, again, control delay and level of service based on delay, and a bicycle perception score for the signalized intersection. For two-way stop control intersections, for automobiles in transit, you can calculate delay and the level of service based on that delay, a volume to capacity ratio, and the 95th percentile queue. For the pedestrian mode, again, you can calculate average delay and level of service. You could also use the two-way stop control method for evaluating mid-block crosswalks, and you can also include driver yielding behavior effects as part of that analysis. So there's a table in the highway capacity manual based on reported research on how often do drivers yield for different kinds of crossing treatments, for example, flashing beacons. So a variety of different techniques that can be used to draw attention to pedestrians potentially crossing the street. You can also use more recent research than what's given in the highway capacity manual if you have more recent data or local data available. For the bicycle mode, for two-way stop control intersections, there's not been a lot of research done, and therefore the highway capacity manual provides only limited guidance for how you can analyze bike operations at a two-way stop controlled intersection. Always stop controlled intersections are fairly similar to two-way stop controlled intersections, except in this case there's also only limited guidance provided for analyzing pedestrian operations. Looking at roundabouts now, again for the auto and transit modes you can get delay, level of service, volume to capacity, and a 95th percentile queue. For the pedestrian mode, the HCM provides guidance to use the two-way stop or mid-block crossing method with care. And for the bicycle mode, the guidance is to analyze the bicyclist either as a pedestrian or as a vehicle, depending on how bicyclists use the roundabout. So which performance measures might you use in analysis? And in this case, the measures that you choose will depend on the analysis purpose and the study area environment. For example, the measures that are based on pedestrian space or circulation area are useful for sizing pedestrian facilities in the downtowns of major cities and for special event planning. I've applied these measures to analyze narrow sidewalks near cruise ship docks in Alaska. So any place where you have large numbers of pedestrians, the space-based measures can be useful. Calculating vehicle or modal delay is the starting point for determining person delay. So if you're interested in the overall delay experienced by all users of an intersection, you can take the vehicle or per bicycle, for example, delay generated by the HCM, apply an average vehicle occupancy, and then convert the vehicle delay into a person delay. The perception scores, which is what we'll be going through next, are designed to facilitate multimodal comparisons. So if the purpose of your analysis is to look at, we have a limited width available for the street and how do we best allocate that among the different modes, then the perception scores can be used to look at how the quality of service goes up or down for the different modes as the right-of-way is allocated differently to the various modes. And then some of the other measures that the HCM provides, such as queuing, in some cases may be a bigger operational issue than delay or level of service. If there's queue spillback from a left turn lane, for example, that blocks through traffic, that's also an operational problem, not just delay. Okay, now we've gone through the different performance measures that the HCM can calculate by mode for urban streets. Now we're going to focus in on the perception scores that the Highway Capacity Manual provides. So I'm going to go through the general framework for those measures and cover the transit and pedestrian modes, and then I'll turn it over to Aaron to cover the bicycle and motorized vehicle modes. So the HCM's multimodal method was originally developed by NCHRP Project 3-70 in the mid-2000s. The development of this method is described in NCHRP Report 616, which is available on TRB's website. We'll also give you a link to HCM Volume 4 at the end of this webinar where you can also download it. This framework, after it was developed, was then tested in a dozen or so different metropolitan areas around the United States. And this testing is described in NCHRP Web-Only Document 158. The purpose of the testing was to get agency feedback on the realism of the results coming out of the method, as well as to get feedback on how easy or difficult it was to apply. And as a result of that feedback, some of the original measures were tweaked a little bit, and that's been reflected in the Highway Capacity Manual. The pedestrian and bicycle components of the multimodal method are based on research that had been previously commissioned by the Florida Department of Transportation and conducted by Sprinkle Consulting. The HCM's multimodal method is designed to evaluate the operational trade-offs of various street designs in terms of travelers' perception of the quality of service provided. So if you take a look at what happens if we restrict on-street parking along a street and convert that space into a bike lane, for example, how does that affect the operation of bicyclists, of pedestrians, of transit users, and of people in motor vehicles traveling down the street? Importantly, the method provides modal perception scores that use a common scale, allowing direct comparisons of quality of service. A common complaint about the Highway Capacity Manual is that level of service C, for example, for one system element, like a two-way stop, does not necessarily mean the same level of traveler satisfaction with another system element, such as a multi-lane highway or a signalized intersection. This multimodal method, however, is designed to use the same scale so that the perception score, say a score of 2.5, means the same level of quality of service or perceived quality of service across modes. And it provides the same level of service letter at the end. Some quick background on how the method was developed. For the pedestrian, bicycle, and automobile modes, video lab participants rated videos depicting various urban street environments. So for example, for the pedestrian mode, there would have been different sidewalk widths, or maybe not even a sidewalk at all. There would have been different levels of traffic adjacent to the sidewalk, different levels of buffering between the sidewalk and traffic, and so on. And the participants were asked to rate service quality on an A to F scale. They were also instructed to look just at what was happening within the street and not what was happening on the side of the street. So adjacent land use, if you have really nice building facades or something like that, that they were instructed to ignore. The purpose of these particular measures is to look at what's within the right-of-way and what's within the direct control of a transportation agency. Regression analysis was used to identify relationships between the various urban street characteristics and participants' ratings. So taking a look at which factors were significant in affecting participants' quality of service ratings and the degree to which these factors were significant. For the on-street transit mode, at first it was tried on-street or on-board surveys to evaluate service quality, but we really couldn't find, or the researchers really couldn't find, a direct relationship between the results that they got for overall quality and the particular service quality features. And it's hypothesized that's because people who choose to ride transit already have some minimum baseline level of satisfaction with the mode, otherwise they wouldn't be using it. So instead, passenger response to service quality changes was measured by looking at actual changes in ridership that have been documented in the literature as frequency increases or as travel speed improves. And that was used instead in developing the transit model. The HCM's models predict traveler satisfaction with conditions on an urban street. These perception scores are open-ended, so they can actually go negative or they can get very high. But in general, lower scores mean better perceived service quality. And to give you a sense of kind of the typical range that these scores fall within, for segments, a score less than or equal to 2 equals level of service A, and a score greater than 5 equals level of service F. So you can get scores much lower than 2 and scores much higher than 5, but typically they'll fall into a fairly narrow range between, say, 1 and 6. The pedestrian, bicycle, and transit scores can be used to determine level of service for those modes. In contrast, the motorized vehicle score is only used for comparison with the other 3 modes, and travel speed is used to determine motorized vehicle level of service. The reason for this comes out of the testing for NCHOP Report 616, where it was found that a number of agencies already used travel speed-based level of service for urban streets and really didn't want to change their standards to fit this new perception score. So for the time being, this motorized vehicle score is used for comparison only with the other modes, but it does use the same scale that the other modes use. So you can still get a direct comparison and still see how much the score goes up and down as conditions on the street change. So now I'll move on to the transit mode. In a HCM context, transit's really only evaluated at the segment and facility level. And the only kinds of transit service that are looked at are those that operate on the urban street. So typically bus, streetcar, and on-street running portions of light rail lines. So if you have a rapid transit line that runs under or over the street, it does not get analyzed using this method. Only modes operating on the street can be analyzed with this method. Also, this particular method is intended to be used alongside the pedestrian, bicycle, and auto perception scores. So if you want to look at other kinds of performance measures for transit, the HCM refers you to the Transit Capacity and Quality of Service Manual, a companion document that provides a wealth of methods and measures specific to the transit mode. For the HCM, for the transit mode is only covered to the level needed to provide a fair comparison with the other modes operating on an urban street. In terms of looking at how the perception score is determined for a segment, the key components of service quality are service frequency, how often does the bus arrive, a perceived travel time rate, which incorporates both the actual bus speed in minutes per mile, as well as reliability, how much extra time do you have to wait at the stop past the scheduled time before the bus arrives. Onboard crowding, because research has found that time seems to pass more slowly, it's more uncomfortable to travel on board a crowded bus versus an uncrowded bus, and so that affects the perceived travel time. And then having amenities at a bus stop, such as a shelter or a bench, help make the time go by a little bit faster compared to having to stand at the bus stop. So all those factors go into determining a perceived travel time rate. Finally, pedestrian level of service also is a factor in determining transit level of service. If you have very good pedestrian facilities leading to the bus stop, then it'll provide a better transit level of service, all other things being equal. And similarly, if you have very poor or non-existent pedestrian facilities, that will lower the overall transit level of service. As a result, the transit measures transit service quality for passengers getting to the bus stop, waiting for the bus, and on board the bus as it goes down the urban street segment. Looking at the facility level, the transit facility perception score is just a length-weighted average of all the segment scores, and this can be converted to a level of service letter. For pedestrian analysis, I'm going to run through some of the key service quality components now. One of these is the sidewalk width, and we set that to 0 feet if there is no sidewalk, but we can still evaluate the pedestrian perception score even without a sidewalk. And typically it will be pretty bad. Another factor that goes into pedestrian analysis is the separation from motorized vehicle traffic, and that looks at the width of the bike lane if one's present, the width of the parking lane if one is present, and the width of any landscape buffer between the curb and the sidewalk. Another factor are barriers that also help to buffer the pedestrian facility from motorized vehicle traffic. This could be, for example, occupied on-street parking. It could be street trees, or it could be any other kind of continuous or semi-continuous barrier that provides a buffer or barrier effect. Another factor is traffic volume and speed in the outside through lane. The more traffic and the faster it goes, then the worse the pedestrian level of perception score will be, and the worse the pedestrian level of service will be that's derived from that score. Now the link score can be used by itself if you want to, or you can combine it with intersection scores to generate a score for a segment or for a facility. Looking now at the signalized intersections, the key factors that affect the pedestrian perception score include the number of traffic lanes that are crossed on a given crosswalk, and you can calculate the score for all the crosswalks at the intersection. How much pedestrians are disturbed by motorized vehicle traffic while they're waiting to cross the crosswalk and as they're crossing the crosswalk. So this includes things like traffic volumes and speeds in the parallel through lane, the total traffic volume that goes over the crosswalk, and then also the permitted left turn and right turn on red volume that goes over the crosswalk. And another factor which isn't present at this particular intersection are the number of right turn channelizing islands that pedestrians pass over as they cross the street. Now for segments, the perception score for segments combines both the link and intersection perception scores, but adds one additional factor, which is the difficulty of crossing the street. How much of a barrier is the street for crossing? So obviously at the boundary intersections, you can use the signal to get across the street, but what if you're in the middle of the street, for example, at this crosswalk here? What the method looks at is how much delay do you experience crossing the street at a legal crossing point, and then compares that to the average delay diverting to one of the boundary intersections to get across the street. And where it says actually the worse of the delay, it actually should be the lower delay, so the better delay in this case. That's actually a little typo there. But the lower delay crossing the street is what goes into street crossing difficulty. As I had said earlier, pedestrian space can also be used to determine level of service, but again, this is only a factor on sidewalks that have really high pedestrian volumes, over 1,000 pedestrians per hour. Going on to facilities, again, similar to transit, facility score is a travel time, is a weighted average of the segment scores. In this case, it's a travel time weighted average. So the segments that you spend more time in get weighted more heavily than the ones that you spend less time in. This is a change from the distance-based weighting used in the Highway Capacity Manual 2010. A few of the other changes that were made for pedestrian analysis. One is the definition of the pedestrian body ellipse, which shows up in Chapter 4 of the manual. The body depth element used for estimating passenger space, or a pedestrian space, has been increased by 2 inches to account for changes in the U.S. population between the 1970s and the 2010s. The basic concept of a body ellipse is that it looks at space taken up by a 95th percentile adult male wearing winter clothing and carrying some sort of small object like a bag or a briefcase, and then giving a little bit of additional buffer so that if the person is standing still and they sway a little bit, they won't come into contact with the person right next to them. So because of changes in the body shapes of people, or at least adult males in the U.S., the body depth has been made 2 inches bigger. Again, the facility and segment pedestrian level of service scores are weighted by travel time and delay. There's also been incorporation of some clarifications in errata that had come up with the HCM 2010 related to link-only analysis and some definitions of intermediate calculation variables. And with that, I will now turn it over to Aaron to go through the rest of the webinar.
All right, thank you, Paul. So I'll lead off with an overview of the bicyclist mode of travel. Like pedestrians, it is also split into intersection, link, segment, and facility analyses. For the bicycle link analysis, the components that have the largest effect include the presence of a bicycle lane. Wider bicycle lanes also will result in a better score than just adding the bike. Amount of separation between the bicyclist and the closest travel lane. The more separation you're able to provide between where the bicyclist travel path is and that outside through lane, the better, the more comfortable they will feel. Traffic volume, speed, and vehicle classifications of the lane closest to the bicycle. So as traffic volume, the speed, and percentage of heavy vehicles goes up, the bicycle's perception of that particular link will go down. Occupancy of on-street parking. Sparsely used on-street parking is a benefit to bicyclists as it provides more room. The more heavily used that parking is, it becomes more of a drawback because now bicyclists have to start worrying about parking maneuvers, and the parking lane can no longer be used as excess room for that bicyclist. And the final primary factor is pavement conditions. So bicyclists really prefer smoother pavement, even more so than vehicles since they lack the shock absorbers. Improving poor pavement quality will result in one of the biggest improvements to the bicycle link analysis result. Bicycle service quality at intersections is influenced primarily by 3 factors, including the cross-street width, bicycle separation through the intersection, and parking maneuvers within the 250 feet of the intersection. For cross-street width, wider intersections are often more challenging to cross for bicyclists. So as the intersection size increases, the bicyclist's perception of the experience through that intersection is going to decrease. The effect of bicycle separation through the intersection and parking occupancy is similar to the link results, where bicyclists at an intersection prefer additional separation from that motor vehicle traffic and fewer conflicts with the parked vehicles. As the separation decreases and parking occupancy will increase, the bicyclist's perception of that experience through the intersection is going to degrade. Similar to the pedestrian segment score, the bicycle segment score is a combination of the link and intersection findings. However, there is an additional factor accounted for in the bicycle method, which is the number of access points on the right side of the road. Access points in this context would be locations generating a large amount of traffic that would be significant conflict points for bicyclists that they need to look out for. For example, a two-way stop-controlled intersect side street or a driveway into a large commercial development such as a grocery store. Like the HCM 2010, the bicycle facility score is a weighted average of the segment scores. Unlike the HCM 2010, though, the segment scores are now weighted by travel time rather than the strict segment length. The HCM was the first, or 2010 was the first HCM edition to actually have the bicycle urban street methodology. While much of the method is similar with the new 6th edition, there have been a few tweaks. This includes the facility score, which was changed to reflect travel time rather than segment length as the weighting factor. Other changes include tweaks to the original method to capture clarifications in errata, and link-only analysis, for example, now uses a level of service scale from the original research rather than the segment scale, basically to return a score that better captured the bicycle experience on the link. In addition to providing a perception score for transit passengers, pedestrians, and bicycles, the HCM also provides the automobile traveler perception score, as Paul was discussing earlier. This performance measure is not the official level service metric for the vehicles on an urban street, but it does allow for that more direct comparison with the other 3 modes. It is only available at the segment and facility level and is based primarily on lane configuration at the downstream intersection, which would result in how many stops per mile that automobile might take while traversing the corridor. So now that we've covered a bit about what goes on under the hood of the multimodal analysis methods for urban streets, I'll share with you a couple of example applications of how you might be able to use these methods. We'll then summarize what we have covered and have some time for any questions you might have at the end. I'll cover 3 potential applications of the multimodal methodology. The first, we'll look at how we can be used for what we call here in California a general plan, but other states call it a comprehensive plan. I'll then present on how the city of Jacksonville, Florida used the pedestrian method to develop more of a baseline data set for the region in terms of their pedestrian level of service for different corridors. And finally, I'll present a road diet application where it was used to assess impacts of a road diet to the 4 different modes. So the first application is how to use the multimodal methods described to assist in, say, transportation planning. This work was done for the city of San Pablo here in the San Francisco Bay Area for their 2030 general plan, where they really wanted to incorporate more complete street policies into their guidelines. To incorporate these complete street policies, the city wanted to move away from developing roadway classifications based on how many vehicles it would carry and develop more multimodal designations. Therefore, the typical arterial and collector designations were replaced with mixed-use boulevards, urban arterials, auto arterials, and avenues. The preferred right-of-way configuration for each designation was then defined within the plan. In total, they came up with 6 different classifications of roadway, which would include state highways, the auto arterials, urban arterials, mixed-use boulevards, avenues, and local roads. Auto arterials, for example, are defined as 2- or 4-lane facilities that prioritize vehicles. Bicycle and pedestrian movements are secondary but not prohibited, and sidewalks are required on at least one side of the roadway. Mixed-use boulevards, for example, though, provide access to retail, commercial, and high-density residential land uses, while facilitating traffic to the freeway network and through the city. All modes of travel share the roadway, but vehicle and bicycle access are not as high a priority as the transit and pedestrians. With a new hierarchy that allows the city of San Pablo to prioritize modes other than the auto, a new methodology that could compare the various modes on an equal footing was needed. Therefore, the city used the multimodal methodologies described today to provide an analysis tool to assess whether proposed changes to the transportation system followed the new guidelines for prioritizing different modes depending on the roadway's designation. The multimodal methodologies could then be used to look at different roadway improvements and prioritize these that prioritize those that better met the goal of that individual facility. Mixed-use boulevard, for example, prioritizes pedestrians. So implementation of pedestrian improvements such as curb extensions, crosswalks, and rectangular rapid flashing beacons would take priority over auto and bicycle improvements like adding turn lanes or adding a bicycle lane. So the benefits of using the multimodal methods described on this project allowed for an evaluation of baseline level service results for all travel modes and the ability to set reasonable level service standards for the 4 different automobiles, pedestrians, bicyclists, and transit passengers. Multimodal roadway designations could be set while the multimodal methods were used to prioritize roadway improvements and better inform mitigation measures for any future development that might come along near these streets. The second application was performed for the city of Jacksonville, Florida as part of their 2030 mobility plan. The city has been ranked as one of the most dangerous cities in the country for pedestrians. So in order to prioritize where to make improvements to the pedestrian infrastructure, the city first needed to determine what the current conditions were on all the major roadways within the region. Pedestrian infrastructure within the city of Jacksonville can range from locations with no sidewalks and no choice but to walk on the road, as shown in the top picture, to tree-lined boulevards providing ample separation between and physical barriers between pedestrians and the motorized vehicles, as demonstrated in the bottom picture. Cataloging which streets had poor pedestrian level service under existing conditions would allow the city to determine which streets required the most resources. Jacksonville ran the pedestrian multimodal level service analysis on each of the major streets within the city and then mapped the results in a color-coded graphic. Using a combination of this database and other information such as collisions allowed the city to determine where the need for pedestrian improvements is greatest. This allowed for more targeted improvements where tight financial resources could yield the biggest returns. Our third and final case study comes from the city of Pasadena, California, and is a project-specific application focusing on a road diet for Orange Grove Boulevard. The multimodal methods were used to quantitatively assess the trade-offs among the vehicle, pedestrian, bicycle, and transit modes that would occur by removing a travel lane in each direction in order to implement the bicycle lanes. And the way we came about finding the multimodal methodology for the city of Pasadena was really wanting to have a quantitative method to address the concerns of various stakeholders on the corridor, including how much will the auto mode be affected by the reduction in lanes and what will be the corresponding improvement to the bicycle mode. Basically, is it worth it to take off a vehicle lane in order to improve the bicycle access? Additionally, they wanted to see, are there any effects on pedestrian or transit mode as a result of this road diet? As a background of the proposed road diet, Orange Grove Boulevard is about 1.6 miles between North Hill Avenue and Sierra Madre Boulevard, with a total of 4 travel lanes and an average daily traffic volume of about 11,200 vehicles. With 11,200 vehicles, it appeared to be a good candidate for a road diet based on the rough rule of thumb that 1 travel lane in each direction should be able to carry about 20,000 vehicles per day. The total cross-section of the roadway is about 70 feet curb to curb. Today, this space is currently allocated as a 2-way left turn lane, 2 travel lanes in each direction, and shoulder parking on both sides. The road diet would remove a travel lane in each direction and replace it with a bicycle lane, and then the remaining space would then be devoted to a little bit wider median. As you can see from the picture, the real primary issues with Orange Grove Boulevard in this area is that it has a significant amount of right-of-way for a relatively light traffic volume. The wide street leads to higher auto speeds that can make biking uncomfortable with the lack of designated bicycle facilities. Additionally, the wide roadway width detracts from the neighborhood feel of this street, which actually has single-family homes on both sides of the roadway. This picture just provides a little bit of a view of what the bicyclist perspective is like. The 11-foot outside lanes and higher vehicle speeds can make it a little uncomfortable for the bicyclist. In this section, it seems to be okay because they're actually riding in the shoulder of where the parking is, but if you move up the street a little bit, there's actually a car parked there. So this would require the bicycles to merge over and conflict with the motor vehicle volumes. The pedestrian experience is a little better than the bicyclist. The shoulder parking and street trees actually help provide that physical separation and a physical barrier between the pedestrian and the higher speed vehicle traffic. However, these higher vehicle speeds do have a negative impact on the pedestrians walking along the corridor. Nobody really wants to walk along a high-speed corridor in the middle of a residential neighborhood. So how would the road diet on Orange Grove Boulevard affect the various modes? Well, the auto mode, as anticipated, became worse. However, the perception score only decreased by between, say, 6 and 10%. This worsening was primarily the result of that slowing down of the vehicle due to the one travel lane rather than two. The transit mode showed a slight improvement to the transit perception score of about 1%, so it's fairly flat. Transit passengers were negatively affected by the decrease in auto speed since the bus is now going slower on its route. However, they were positively affected by the improvement to the pedestrian environment prior to accessing the bus, since all transit passengers start out as pedestrians. As anticipated, the bicyclists showed the biggest improvement, going from level service C to level service B, which equated to about a 20% improvement to the perception score. The slower auto speeds in the exclusive bike lane were the primary drivers of this improvement, but the decrease in the number of through lanes, however, did increase the number of vehicles in the lane closest to bicyclists, which had a slight negative effect on the actual score. It's still positive, and it would have been higher if we hadn't concentrated all the vehicles into the lane closest to the pedestrian, or yeah, to the bicyclist. Finally, the pedestrian experience on the corridor would also be improved by the road diet, with an increase to the pedestrian score of about 9%. The slower auto speeds and increased separation between the vehicle and the pedestrian due to now there's a bicycle lane between them and the sidewalk was mainly responsible for this improvement. Similar to the bicycle mode, though, the concentration of those vehicles when we combined all the vehicles from two lanes into one, which is now closest to the pedestrians, did have a small negative effect. Now we'll move into a kind of a brief summary and wrap up before answering any questions you might have on what we presented today. So as we demonstrated, the Highway Capacity Manual covers much more than highway capacity. The multimodal methods we touched on allow for analysis of motorists, pedestrian, bicyclists, and transit passengers together. These can be performed at a variety of levels, including the intersection, the roadway links between intersections, or a combination of the two. It is also important to note that no one tool or performance measure can really tell the whole story of various streets. Other aspects such as safety, accessibility, and network connectivity must be considered. However, I believe the true strength of the HCM for multimodal analyses of urban streets is the ability to compare the four modes using a similar approach methodology that will allow for a more quantitative assessment of what design choices will do to the various modes. So while a significant amount of work has gone into these methods, these methodologies are continuing to be refined with subsequent releases of the Highway Capacity Manual and new research. Areas of improvement, the next version of the HCM that the committee is looking into include incorporation of missing system elements. This would include having roundabouts, all-way stop signs, ramp terminals, or other alternative intersections as part of the analysis corridor. Currently, we can only really look at two-way stop and between signalized intersections. We're also looking into improving the pedestrian density methods to really better meet the needs of our largest cities, such as New York. Really, density in New York is going to be far more of a driver of the pedestrian experience than whether there's a street tree or on-street parking. Finally, we would also like to point out that the fourth volume of the Highway Capacity Manual, which can be found online for free, contains a number of the useful resources that Paul was mentioning. So NCHRP Report 616 documents the development of the multimodal methods, while the web-only document 158 goes into detail about those field tests and how the methodology tested. TCRP Report 165 is that Transit Capacity and Quality of Service Manual, and it's a great tool if you are looking for more detailed analyses of performance measures for transit. And with that, we'll move into the questions section.
Great, thank you so much. There's some really great presentations, and so now we will move into our Q&A. So if you haven't already, we have received numerous questions that have come in, so we'll try to answer as many as possible over the next 20 minutes, and then I'll go over how to earn PDH credit at the end of those 20 minutes. So I'll go ahead and get started. If there's multiple attendees at your site, have them write down their questions for you, for the host, and for the host to type into the question pod. All right, so I'll go ahead and begin. Do you believe that the new highway capacity manual tools for multimodal analysis are user-friendly for planners who are not engineers? Planners usually end up reviewing corridor studies or TIAs, but sometimes have trouble comprehending how some of the findings are developed.
Well, I guess I'll take that one. I guess in terms of applying the method, some of the concerns that have been brought up about the method as it was presented in the HCM 2010 is that it requires a lot of data to measure these or come up with these perception scores. However, a lot of these measures are either things that you would need anyway to do automobile analysis, but in this case the question is specific to planners, and they may not be doing they may be concentrating only on pedestrians or bicyclists or both. And in that case, a lot of the measures can also be defaulted if you don't have specific information. But a lot of the information that is needed is readily available from a variety of sources, whether it's from aerial photos, or from traffic volume counts that the local transportation agency would have. So the main factors are really traffic speeds, which you can get from a posted speed if you don't have actual speeds, volumes, and the presence or absence of major facilities like a sidewalk or a bike lane. Those are the main things that affect the calculation of the measures. So data doesn't have to be a problem. You can make it as detailed as you want, but you can also simplify it if you don't have all the data in hand to calculate the measures. The purpose of having a numerical score that can go up and down and that can be compared to each other was intended to make it simpler for both professional staff and for laypersons to understand what's going on. You can see how much the number goes up and down. Another complaint you might say with the level of service system is that sometimes a small change in the underlying performance measure can result in a one-letter change in the level of service, which implies a bigger effect than there really was. And by reporting both the score or just the score and level of service or the score by itself, then you can see just how much did it change. And you can see from Aaron's presentation for Pasadena, in some cases it changed a little bit, and sometimes it changed by quite a bit. So you can get a sense of the magnitude of the change in quality of service through this method.
And then I would say, as Paul was alluding to, I think having the score is a little more easily understood by planners where they don't have to worry about some of the other level of service metrics like freeway density, for example. I mean, what does it mean to have 45 passenger cars per mile per lane? So by having a score, and that's based on more of a user perception base, it's a little more intuitive, I think, to understanding what's going on in the corridor.
Great, thank you. Another question that has come in. What is the significance of the color green or blue for the check marks and text on slides 15 to 20?
Okay, on those slides, the color green indicates measures that are used to determine level of service. The other ones that were blue or lavender colored are other performance measures that can be calculated for that mode, but which do not are not an input into level of service. In some cases, there may be more than one measure that can determine level of service. There may be a primary measure like control delay that normally is used to determine level of service, but there may be, in some cases, another measure like volume to capacity ratio that if the volume to capacity ratio exceeds 1, then the level of service automatically becomes F. And for that reason, those are also shown in green on those slides.
Great, thank you. What is the most appropriate method for multimodal analysis on a corridor with a shared use path if the path runs parallel to the corridor?
So I'll take a crack at this.
Okay, go ahead.
Or if you want to, yeah,
go ahead.
Okay, so the urban street methodology is really defined or meant for sidewalks that are on an urban street. So if you have a shared use path, I guess it really depends on how far off of the street it is. If it's separated enough that it's almost its own entity, there's another methodology within the highway capacity manual that calculates the level of service of that shared use path. However, if the shared use path is acting more like a typical sidewalk would on the street, then you would want to be using the multimodal methods that we described today.
Chapter 24 covers shared use paths, and the introduction to that chapter provides some guidance on when would you use the shared use path method versus the urban street method. And in general, the cutoff is around 35 feet separation between the path and the street, although that's not a hard and fast rule. But basically, research has found that at least out to 35 feet, that the motorized vehicle traffic on the street has some impact on user perceptions of quality of service. But you could have, for example, a shared use path in a freeway corridor with a sound wall between the freeway and the path where the path is only 10 feet away from the freeway facility. You could treat that as a shared use path, but a side path along an urban street with a 10-foot landscape buffer, that would be considered a part of the urban street.
Okay, for two-way stop control for pedestrians, what would you be measuring? The pedestrian crossing the major road or the pedestrian crossing the major unsignalized driveway?
And here you'd be measuring the pedestrian crossing the major road. The assumption in the method is that the people on the side street or the driveway have to yield both to the pedestrian and the traffic on the street. So although we know it's not always the case, the major delay to pedestrians is crossing the major street and looking at the barrier effect of the major street.
Okay. What genius decided to make the numerical scores go down when perceived level of service improves? Engineers are confusing enough with bizarrely constructed metrics making it worse. Any response to that?
Okay, well, I'll take this one too. I suppose someone could do it either way. I think the original method, looked at, you could rank something, where 1 is best and 10 is worst. It just depends on what scale you choose, and the way that the research for NCHP 370 did it was to make a low number represent a better score.
Great, thank you. Is vertical separation a component of the bicycle analysis for separated bicycle lanes or protected intersections?
So vertical separation isn't explicitly called out as a separation, but you can look at it in terms of, it does look at how much room there is between the bicycle lane, the outside travel lane, and the shared, or the shoulder, basically. So as that gets wider, the bicycle's experience gets better. In terms of actually accounting for, say, separated bike lanes or barrier-separated bike lanes and the protected intersections, these are all kind of newer things that have come along since this research was done a number of years ago. So we don't explicitly account directly for it. If you have like a buffered bike lane, for example, one way I've been doing that as a proxy is to just make it a wider bicycle lane. However, I just caution that there actually hasn't been research into the real effect on a bicyclist's perception of having the buffered bike lane or the protected bike lane, so we can really quantify something to put into the highway capacity manual. I would say this is one of the research areas that we'd like to really look into as we progress into new research for the next update.
Yeah, as with many things in the highway capacity manual, you need to have enough facilities already existing before you can study them and get results that you're comfortable enough with that they can be put into the manual. And so, in the mid-2000s in the US, there just weren't that many cycle tracks or other types of vertical separation on US bike facilities that you could use for modeling. That's probably not the case now.
Great, thank you. How does the bicycle perception score account for protected bicycle facilities and lanes? In particular, parking protected bike facilities where parking is left of the bike facility. Sorry. Should I reread that question?
Well, basically this just goes back to the question that we were just addressing, where some of these new types where you actually flip the parking and the bicycle lane, where you're using the parking to protect the bicycle lane, that's kind of a newer thing that people are starting to do, and we don't really have the research on it yet. So as we build more of these, we'll be able to get a better data set to come up with and update the methodology to account for that.
Great, thank you. What calculation tools were used on the Jacksonville and the California Road Diet Study? HCM6, spreadsheets, which did HCM methods like hcmvolume.org?
I'm not exactly sure of the Jacksonville method. My guess is because it's in Florida, they were probably using the Florida analysis tech, or the FDOT Quality of Service Handbook, I think that they have. It's basically the same methodology, but it's just written up in a slightly different way. So that'd be my guess of what they used on that. In terms of the road diet case study in California, it was based on a software program to input, and it's very similar to the spreadsheets that were developed for the actual methodology, as you might find in Volume 4. So you could develop a spreadsheet to implement that as well.
Great. All right. Are there any plans to incorporate a fifth mode as part of the evaluation, namely trucks?
Well, I think you see in this edition of the Highway Capacity Manual that trucks are beginning to be identified as a separate mode. You see that in some of the early chapters, 2 and 3, for example. But again, it's kind of the need for research to identify what level of, what would affect truck performance, and from whose point of view? Is it the truck driver? Is it the shipper that wants reliable travel times? There has been work done to develop a truck level of service. It has not yet made it into the Highway Capacity Manual, not been adopted yet by the Highway Capacity Committee. It does show up in the planning guide that's available on Volume 4. And there's a separate National Cooperative Freight Research Program report, I think it's 31, that describes that method. And maybe Aaron can talk about that a little bit more.
Sorry, I must admit I missed the last one. I was reading a couple questions ahead. Okay,
yeah, there has been work done in that area. There's still more work to do, but I think that it is something, the truck mode is something that's becoming more and more distinct within the Highway Capacity Manual.
Okay, thank you. Are the existence of regulatory signs such as R10 to 15 turning traffic yield to pedestrians at signalized intersections considered in the pedestrian analysis? Do they improve the pedestrian facility LOS?
So actually having signs at intersections is not explicitly as an input into the methodology itself. As Paul, I think, mentioned in the pedestrian section, it's really about how many vehicles are going across the crosswalk, where we're not really considering whether there's a sign that yields. I would assume we're just assuming that most motorists are going to do what the law would require, which is yield a pedestrian in the crosswalk.
Yeah, I think I'd have to go back and look at what was done in the original Florida research. That was kind of the original genesis of the pedestrian method, to see if that was a factor that was considered or not. Because I know they did look at a number of different factors and did not include all of the ones they looked at in the final model.
Okay, what program or software package implements this latest HCM method?
I would say I don't actually know who's implementing it, because I haven't actually looked at the newest one to see if they're implementing the 6th edition, but my guess would be the highway capacity software would probably be getting close if they haven't already implemented this. And then some of the other ones like Bistro or Synchro are probably working on it, but I haven't heard that they've completed it.
Okay. Why do pedestrian LOS calculations not take into account driveways?
Again, this is probably what I'd have to go back and look into the underlying research for it, but my guess would be it's because it was not found to be a significant factor. But again, I can look into that and get back to you to get a more definitive answer on that.
Okay, thank you. All right, and for pedestrian conditions, why wouldn't the number of driveways be a factor as it is used for bicycle conditions? Also, the condition of the sidewalk could be a factor, tripping hazards, missing panels, lack of ADA ramps, but not incorporated here.
So this is probably, as Paul mentioned, it's probably a factor that just didn't rise to the top of things we're looking at. We're trying to do a methodology that wasn't quite as data intensive and find the factors that were the biggest effect on pedestrians. I would say, obviously, tripping hazards, missing panels, lack of ADA ramps, that's kind of a high end, and I would say that's where we're getting into. Also, in terms, you don't want to use the multimodal performance measure as your only tool, but you want to be looking at other aspects such as safety. So if you have tripping hazards, missing panels on a particular sidewalk, then that would have to be factored into what you're doing in terms of, let's say you're doing a road diet. I would say that would be an impetus for replacing the sidewalk.
And the method is also specifically not intended to be used for an ADA analysis to see if a facility complies with the ADA. It's looking at general operations, but not at does it meet the ADA requirements or not. You'd have to look at that separately.
Great. Do you see including measures for freight and or urban service vehicles in future HCM versions?
I think as Paul alluded to earlier, we're starting to incorporate a lot more freight and truck aspects into the highway capacity manual. There's a lot of freight research going on. So I definitely would say as we move into future HCM versions that there will be a lot more in there on trucks and truck level of service.
Great. For perception scores, are they calibratable sorry, for experiences for people perspective in different cities?
In the original research for NCHRP Report 616, they looked at location as a factor. The scores were tested in different sized communities around the United States, and there were at least 4 test sites. So like Oakland, California, I think College Station, Texas was one, but different locations, and they did not really find that the location made a significant influence on the results. I would go into at least not enough to include in the model. You can go into report 616 and it will go into more details about how that was evaluated. But in general, they found that they were getting similar results no matter which test site they were getting the results from.
Great, thank you. We'll ask one more question before we go over how to earn PDH credit one last time, and then we'll return to the questions for another 5 to 10 minutes. It looks like we have 5 or 6 more questions that have come in. So I wanted to go over how to earn course credit first, but let's answer one more question before we do that. With the new HCM 6th edition, are the LOS thresholds for urban streets and intersections based on newer research?
Here, the thresholds are based on the same underlying research from NCHP Report 616. The one difference is that when you're doing a link-only analysis, the scale is a little bit different than what was in the HCM 2010. It was found that in converting the method to the HCM and making it a little bit more consistent, there was the same scale was applied to links and segments, which really wasn't the intent in the original research. And so you're getting some unrealistic results as a result. So the intent with making the change in the scale for link analysis is to get back to the results from the original research and provide a little bit better results.
And I will say I think there is a little bit of newer research into the methodologies for pedestrian and bicycle, but I would say that's just kind of minor tweaks. We released it in the 2010. We got some feedback that there were some slight issues under certain situations, so a small amount of additional research was done in order to perform small tweaks to the actual methodology. But there's no real main wholesale change to thresholds or any significant new research that was added.
Great, thank you so much. So we still have a few questions to get through. I wanted to go over one last time for those who need to run off. To earn course credit today, you will need to verify your attendance. So write down these event attendance codes. If you registered for the entire 8-part webinar series, as a bundle, you'll use the code 100180. If you registered for today's webinar only, you'll use 100200. Individual and bundled registrants will go to www.it.org/learninghub, log in, enter the event attendance code into this box that looks like this, and it's located on the same page as when you log in. You just scroll all the way down to the bottom of the web page, and it's in the right-hand column below the calendar. You enter in the code into the box, a survey will launch, complete the survey, and once you do so, you should be able to view and print your PDH e-transcript by clicking the icon at the top of your Learning Hub that looks like a certificate here in this picture. If there's multiple attendees at your site and they're not registered for today's webinar, the registered host will receive an email 1 hour following today's webinar with a link to forward to the multiple attendees at their site. Each additional attendee is responsible for a PDH processing fee unless they are a state DOT or FHW employee. The state DOT and FHWA employees will use the same promo code provided to the host to register for today's webinar or the entire bundle. Once the attendees have made their payment or used the promo code, they'll be able to then use the same event attendance code as if they were a registrant for today's webinar only, 100200, and use that to take the survey, and the PDH transcript, the credit will appear in the PDH e-transcript. Okay, and then just a warning, if the additional attendee is not a IT member or has not previously attended an IT webinar, they may need to create a non-member account in order to receive the PDH credit. All right, so now we'll go back to our Q&A. Thank you everyone who, all of the registrants and attendees today. If you have to run off, thank you so much for joining us. And we'll get to these last few questions that have come in. Hold on one moment. Okay, for segment perception scores, how are the link and intersection scores combined? By sum, average, etc.?
So it's actually an equation that was developed in the original research. So it's a combination of a weighting factor times the individual intersection score plus a weighting factor for the link times a weighting factor. And then if there are any additional components, such as the number of access points, for example, that was a component of the bicycle method.
Okay. How are the facility scores time weighted? Unless simulated, the travel time should be based on distance, or are intersection delays for traffic controls get included to influence travel time within facility? I.e., how is the travel time calculated for facility?
Yeah, it's the second part of that. The intersection delays due to traffic control are included as part of the segment and facility time weighting. So if you have a long delay at you have two arterial streets crossing each other, and it's a 3-minute cycle length, and you have a very long pedestrian delay getting across, that'll affect. So you have to wait on the street corner with cars going by on two sides. That's a less pleasant environment than having a short wait at an intersection. So that's one reason why it was changed from distance weighting to time weighting. But I mean, you're correct that a lot of the time just going through the segment, the time will be proportional to the distance. But then when you get to the intersection at the end, you will have some difference in how much time you wait at the intersection.
Great, thank you. Can you please elaborate on the weight ride score for transit?
So the weight ride score gives you a value of 1 for a transit service that operates at 1-hour headways and in most cases has a average travel speed of 15 miles an hour. And as you improve on that, then you get a higher weight ride score. And the number that you get represents the ratio in terms of increased ridership you would expect to get for a more frequent service or for faster service. And so there's been research done on the ridership change that occurs when you increase the frequency or decrease the frequency and as speed changes. So that that all's been incorporated into the weight ride score. So if you have 2.5 for the score, it would mean that you would expect to get 2.5 times the ridership for that particular transit service compared to the baseline of hourly headways and 15-mile-an-hour speeds. It doesn't tell you what the ridership would be. It's just a factor of compared to the baseline service.
Great. How do we know that commercial software faithfully and completely implement the HCM methods? Are we to rely on a vendor's promise, or does someone certify the software is good to go?
So I'll start out that one by saying the Highway Capacity Committee doesn't actually certify any software as the official methodology. So they're all kind of out there developing based on what they see in the Highway Capacity Manual. In terms of determining who faithfully and completely replicates the HCM methods, it's kind of up to the user to understand what's in the highway capacity manual and check it against what's in the commercially available software. For the urban streets methodology for bikes, peds, and transit, it's actually it's an easier method than, say, what you might get into for a detailed intersection level service analysis, in that you can replicate it, what's in the highway capacity manual, in a spreadsheet itself, so you can use that to check what's going on with the commercially available software. For the most part, the commercially available softwares are usually fairly close, but you usually get slight differences even when doing the exact same corridor between the different versions of software, just due to some rounding errors and other items.
And you can run the example problems in the HCM against the software to see if they come up with the same answer or not. That's one way of checking it.
Great, thank you. We have a comment that has come in. First prize is a better prize than second prize, but 2 is a higher number. A is a better grade than B, but A is the first letter of the alphabet and B is the second, so B is the higher letter. Of course, it could be done either way, but the way chosen has plenty of precedent and understanding. So thank you for that.
I think this is getting back to that earlier comment. So yeah, there's a couple of ways of looking at how you set your scores.
Yeah, great. Thank you. Are unmarked crosswalks considered legal crossing points for the purpose of the PED segment diversions analysis? Or, let's see, oh, no, never mind. So that was their question.
Basically, any place where you can legally cross the road, if you can do that in the middle of the segment, then you can apply the segment diversion analysis. So an unmarked crosswalk would be considered a legal crossing point. If pedestrians are specifically prohibited from crossing the street, or there's a barrier down the middle of the median, or for some other reason you can't do that, then you would have to divert and incur that delay getting across the street, then getting back to where you were on the other side.
Great, thank you. Lower scores are equal to good are likely related to the fact that these scores are seemingly related to travel times. Is that correct? It is a bit funny that travel time is maintained as a standard consideration, given the goals of a complete street are generally more diverse than vehicle travel time.
Well, travel times don't go into the calculation of the base link or intersection perception scores. They're only used for doing a weighted average for the facility analysis. So if you're combining the links and intersections up to segments and then the segments up to facilities, then the amount of time you spend in each segment, the more time you spend in a particular segment, then the more that weights on the overall facility score. But that's really the only way the travel time enters into the perception scores, at least for auto, well, at least for pedestrian and bicycle. For transit, it does enter into it because it is an important ridership component. There is a ridership effect of having very slow bus service, for example. So it just depends on what came out of the basic research in terms of what people found, what was found to be significant in influencing people's reactions to their perceived quality of service.
Great. So we have one more. This is a follow-up on your comment about the commercial software. This attendee is looking for a better answer, it seems. And he says the need for users to check the adequacy of software, so the following up on your comment about commercial software and the need for users to check the adequacy of this software, that is just not practical or possible with the complexity of the methods now. That's just not a great answer, is what this person said. So do you have a response to that?
Well, I think you have to look. Go ahead, Aaron.
Well, I was just going to say I agree in some ways that it would be nice to have an officially sanctioned method or software, but that could lead to more problems, and the committee's tried to back away from actually saying any one software is the approved one. You can give a bunch of case studies that may have, as Paul referenced, there are some example problems that if you put into a different software, they should return the results that are reported in the HCM. However, there's so many different types of configurations of roadways that you're never going to be able to come up with a comprehensive data set to test and figure out which one is implementing the various methods. So it just gets kind of complicated, and honestly, this is a big discussion of numerous committee meetings sometimes about having an official methodology and whether we want to come up with more case studies that they can test their software against. Needless to say, I'm sure it'll be an ongoing issue, and perhaps in the future we might come up with an idea, but for now, it's just it's almost up to the user.
There's also TRB policy considerations that the committee can't be seen endorsing particular software packages. So as to provide some sort of guidance to the user, that's one reason why we have the example problems now. And as Aaron said, there has been discussion in the committee about can we do more in terms of just, here are the inputs to the method and here's the answer you should get at the end to provide additional ways of testing. I understand what the commenter is saying about that takes a lot of time and you may not have the time or resources to do it, but the committee is kind of tied by TRB policy in that they can't be seen endorsing particular commercial products.
Great, thank you. So that is all of the questions that have come in for today's webinar. So thank you all. Those were really great questions and comments. So thank you so much for participating. Thank you for registering.